124 light years from where you're sitting right now, there is a planet that, according to some of the data collected by the James Webb Space Telescope, might be covered by a single global ocean, wrapped in a thick hydrogen atmosphere, orbiting its star at almost exactly the right distance for liquid water to exist. And somewhere inside that atmosphere, Webb detected the chemical fingerprint of a gas that, on Earth, is produced almost exclusively by one thing: life. This is the story of K2-18b, the exoplanet some astronomers now believe might be the closest thing to a second living world humanity has ever found, and why the scientists who found the signal are almost more cautious about it than anyone watching from home. Picture what that planet might actually look like, based purely on what the data allows, not a rocky, cratered surface like Mars or the Moon. Instead, imagine a deep blue-gray horizon with no land anywhere in sight. A single unbroken ocean stretching the entire circumference of the planet, capped by a thick, hazy hydrogen sky many times deeper than Earth's own atmosphere, dimly lit by a small, cool red dwarf star hanging low and reddish in that sky. That's the visual astronomers reach for when they describe a Hycean world, and it's important to say plainly that it's a model, an informed illustration built from chemistry, not a photograph. No telescope humans have built, including Webb, can directly image the surface of a planet 124 light years away. Everything we know about K2-18b comes from a single, much subtler technique. The story begins in 2015 when NASA's Kepler Space Telescope, on an extended survey after its original mission had ended, picked up a faint, repeating dimming in the light of a small, cool star known as K2-18. Something was passing in front of it every 33 days, blocking a tiny fraction of its light each time. That's the standard signature of a planet in orbit, and this one turned out to be roughly 2.5 times the size of Earth, and about 8.5 times its mass, placing it in a category astronomers call a sub. Neptune, bigger than any rocky world in our own solar system, smaller than gas giants like Neptune or Uranus. For years, that was more or less all anyone knew about it: a size, a mass, an orbital period, and one detail that made it worth another look: the distance of that 33-day orbit placed the planet inside its star's habitable zone, the band of distance from a star where temperatures could allow liquid water to exist, on a planet's surface, assuming the right conditions were there to hold on to it. That single detail was enough to put K2-18b on a shortlist. Picture how astronomers actually extract chemistry from a planet they can't see directly. As K2-18b passes in front of its star from Webb's point of view, a sliver of starlight grazes through the very edge of the planet's atmosphere before continuing on toward Earth. Different gases absorb very specific slices of that light, like a barcode written in wavelengths instead of black and white lines. By capturing that starlight and splitting it into its full spectrum, astronomers can read which gases left their mark on it, molecule by molecule, without ever needing a picture of the planet itself. In 2019, teams using the Hubble Space Telescope applied that same transit technique to K2-18b and found hints of water vapor woven into that light, the first such detection for any planet sitting inside a habitable zone around another star. It wasn't proof of oceans or rain or clouds, but it was the first thread pulling K2-18b out of the enormous, undifferentiated pile of sub-Neptunes and into a much smaller group of planets worth watching closely. Then Webb came online. The picture started getting stranger and more interesting. At almost the same time, researchers led by Niku Madhusudan at the University of Cambridge used Webb's infrared instruments to take a much deeper look at K2-18b's atmosphere in 2023. And what came back didn't look like a typical gas giant's chemistry at all. They found methane and carbon dioxide in meaningful quantities, but almost no ammonia, a combination that, according to modeling, fits neatly with a very specific kind of world. One with a thick, hydrogen-rich atmosphere sitting directly on top of a deep, planet-spanning liquid water ocean. Madhusudan's team gave that category of planet a name: Hycean, a combination of hydrogen and ocean, describing a world that might not look anything like Earth up close, but could, in principle, support the same basic chemistry that life on Earth depends on. That same 2023 analysis contained something else, a faint signal that the team was careful not to overstate at the time, a possible trace of a molecule called dimethyl sulfide, DMS for short. On Earth, DMS is produced overwhelmingly by marine life, specifically by phytoplankton, the microscopic organisms that carpet the surface layers of our oceans. It's part of the reason the seaside has the particular smell it does. Outside of biology, there's no well-established process that produces DMS in large quantities. That first 2023 signal was too weak to draw any real conclusion from, but it was enough to justify pointing Webb back at the same planet, with a longer, more sensitive follow-up observation. That follow-up came in 2024 and 2025, using a different instrument on Webb called MIRI, the mid-infrared instrument, which can pick out chemical signatures that Webb's near-infrared instruments can't see as clearly. And this time, the DMS signal came back stronger, this time alongside a related compound called dimethyl disulfide, or DMDS. Announced in April of 2025, the detection reached what statisticians call 3 sigma significance, a way of expressing how confident researchers are that a signal is real and not just a fluke of instrument noise or data processing. 3 sigma roughly translates to about a 1 in 700 chance that the signal is a random accident. That sounds convincing, and in most fields of science, it would be treated as a real result. In astronomy, and especially in a claim this consequential, the bar is set deliberately higher. Discoveries of this magnitude are typically only accepted at 5 sigma confidence, a threshold so strict it corresponds to roughly a 1 in a few million chance of being a coincidence. 3 sigma gets you a serious hint. It does not get you a discovery. It's worth pausing to note that this wasn't the first time K2-18b generated exactly this kind of excitement, and the earlier round is a useful preview of how this current chapter might unfold. When the initial faint DMS hint surfaced back in 2023, headlines around the world ran well ahead of what the underlying data actually supported, with some outlets describing the detection in far more definitive terms than the researchers themselves ever used. The scientific backlash was swift. Multiple independent groups reanalyzed the same raw Webb data and found the original signal was weak enough that it could just as easily be noise, and the whole episode became something of a cautionary tale within the exoplanet research community about the gap between a promising hint and a confirmed result. That history is part of why the 2025 announcement, this time built on stronger, MIRI-based data reaching 3 sigma confidence, was framed by its own authors with so much visible caution from the very beginning. They had already watched what happens when a preliminary signal gets treated as a final answer. The researchers behind the finding have been unusually open about that distinction, and it's worth sitting with exactly what they've said, rather than rounding it up into something bigger. Madhusudan's team has described this as the most promising sign yet of a possible biosignature beyond our solar system, while explicitly stopping short of claiming they've found life. Other scientists in the field who reviewed the same data independently have used the word candidate, and one of them, MIT's Sarah Seeger, has said publicly that a signal like this may simply remain in that candidate category indefinitely, meaning astronomers may never fully close the loop between detecting a molecule and confirming what's actually producing it, tens of trillions of miles away, using nothing but the faint starlight leaking through a planet's atmosphere. And that caution turned out to be justified almost immediately because within about a year, a separate team of researchers at the University of California, Riverside, published a study specifically testing whether DMS could be produced without biology at all, using detailed atmospheric chemistry models built around the same hydrogen-rich, high-sulfur conditions astronomers believe exist on K2-18b. That team found that certain non-biological photochemical reactions, chemical processes, driven purely by starlight interacting with sulfur compounds already present in a hydrogen atmosphere, could plausibly generate meaningful amounts of DMS without any organism involved anywhere in the process. Picture sunlight from K2-18's small red star striking the upper layers of that thick hydrogen envelope, breaking apart existing sulfur-bearing molecules and letting the fragments recombine into DMS through pure chemistry. The same way sunlight drives reactions in the hazy atmospheres of Saturn's moon Titan or the outer layers of Jupiter, just with a different mix of starting ingredients. That kind of pathway doesn't require a single living cell. It just requires the right molecules already being present in the atmosphere and a star bright enough to power the reaction. It doesn't disprove the biosignature interpretation. It does mean the sentence, DMS equals life, no longer holds up as a clean, one-to-one rule the way it effectively did on Earth, where biology is the only significant source anyone has ever confirmed. Off Earth, in an atmosphere unlike anything in our own solar system, the chemistry might simply work differently, and researchers on both sides of the debate have said the honest answer is that nobody yet knows for certain which pathway is actually happening on K2-18b specifically. There's an even more fundamental disagreement sitting underneath all of this, and it's easy to miss if you only hear the headline about the gas. Not every researcher studying K2-18b agrees that it's a high sea and ocean world at all. Some competing models suggest the planet could instead be something closer to a scaled-down gas giant, or a world with a deep magma ocean beneath crushing pressure, rather than liquid water, environments that would make the entire premise of a habitable surface effectively meaningless, regardless of what gases show up in the atmosphere above it. Picture that alternative version for a moment. Instead of a calm, dim ocean horizon, a planet with no true surface at all, just atmosphere thickening gradually into searingly hot, high-pressure fluid, then eventually into molten rock, with no boundary a person could ever stand on, even in principle. The size and mass that first drew attention to K2-18b are consistent with several very different possible internal structures. And right now, astronomers can't fully distinguish between them using the data available. The High-Cean hypothesis is the most exciting version of this planet's story, the one that gets the headlines and the illustrations. It is not the only version that fits the numbers, and researchers modeling the alternatives have been careful to keep reminding the field of that every time the DMS story resurfaces. So here's an honest way to hold all of this at once, because that's really the only way to hold it responsibly. Somewhere around a small, cool star 124 light-years away, there is a planet where NASA's most powerful space telescope has detected a chemical signal that, if it originates the way it does on Earth, would be one of the most significant discoveries in the history of science. That same telescope, and the scientists analyzing its data, have also been explicit that the signal isn't yet strong enough to rule out non-biological explanations, that the planet's basic structure is still genuinely disputed, and that even the researchers who found the signal in the first place have publicly declined to call it evidence of life. Both of those things are true simultaneously, and neither one cancels the other out. What happens next isn't a cliffhanger manufactured for effect. It's the literal, scheduled next step in the scientific process. Webb has additional observing time already allocated to K2-18b, specifically designed to either strengthen that 3 sigma signal toward the 5 sigma threshold that would make it a genuine discovery, or weaken it into statistical noise as more data comes in. That follow-up work isn't just more of the same observation repeated for luck. Researchers are specifically hunting for additional independent molecular signatures that could help settle the abiotic versus biological, question outright, chemical byproducts that photochemistry alone would be expected to leave behind, but that biology typically wouldn't, or vice versa. Finding, or conspicuously failing to find, those secondary fingerprints could end up mattering as much as the DMS signal itself. Every additional hour of telescope time pointed at that planet either sharpens the picture or erases it. There's no version of this story where the current 3 sigma result simply stays where it is forever, unresolved. The next several years of follow-up observations are expected to move it decisively in one direction or the other. It helps to put K2-18b next to the other most watched habitable zone candidates. Astronomers are currently studying because the comparison shows just how unusual its situation actually is. The TRAPPIST-1 system, 39 light-years away, has 7 roughly Earth-sized rocky planets orbiting a small red dwarf star, with at least 3 of them sitting inside the habitable zone. Webb has spent significant observing time on several of those worlds, and so far the results have been almost the opposite kind of story. Multiple TRAPPIST-1 planets appear to have thin atmospheres or none at all, likely stripped away over billions of years by radiation from their small, active host star. They're the right size and the right distance in the atmospheres that would make them, promising simply, don't seem to be there in the way scientists had hoped. K2-18b is nearly the reverse situation. It's larger than a purely rocky world, its habitability is far from settled, but it has an unmistakably thick, chemically rich atmosphere that Webb can study in detail, and that atmosphere keeps returning signals worth arguing about. Neither system has produced a confirmed habitable world, but between the two of them, they illustrate the actual state of this entire field right now. Astronomers finally have instruments capable of asking the right questions, and the honest answers keep arriving as maybes rather than yeses or nos. There's a broader shift happening around this story that's easy to miss if you're only following the K2-18b headlines specifically. For most of the history of the search for life beyond Earth, researchers were essentially guessing which stars might be worth pointing instruments at, spreading limited observing time across enormous numbers of candidate systems with almost no way to prioritize between them. That's starting to change. Astrobiology researchers have recently assembled a prioritized shortlist of the most promising known habitable zone planets, built specifically so that instruments like Webb, and eventually next-generation observatories like the extremely large telescope, can focus their limited time on the systems most likely to actually matter, rather than spreading attention evenly across thousands of candidates with no way to rank them. K2-18b sits near the top of that kind of list for an obvious reason. It's one of the only habitable zone worlds where a large space telescope has already returned a signal ambiguous enough to be worth the argument in the first place. Looking further ahead, NASA has begun early planning for an entirely new instrument built around exactly this problem, a mission concept called the Habitable Worlds Observatory, aimed at directly imaging Earth-like planets around other stars and analyzing their atmospheres with a level of detail and sensitivity beyond what even Webb can achieve, where Webb has to rely on the transit technique. waiting for a planet to happen to pass in front of its star and reading the faint chemical fingerprints left in that borrowed starlight, the Habitable Worlds Observatory is being designed to block out a star's glare directly and capture actual reflected light from a planet itself, the same way our own eyes see planets in our solar system, rather than inferring them from shadows. That's a fundamentally more direct way of studying a world. But it demands technology precise enough to blot out a star that can be 10 billion times brighter than the planet sitting right next to it. An engineering challenge that's part of why the mission remains firmly in the planning stages, likely decades from launch. Its entire justification traces directly back to moments like this one, a signal tantalizing enough to matter and just short of strong enough to settle the question outright, sitting in the data from the best telescope we currently have. So where does that leave anyone watching this story unfold in real time? Not with an answer. And it's worth being honest that anyone promising you a clean answer right now is skipping past the actual science to get to a more satisfying ending. What it leaves you with is something rarer than an answer. A live, open question, sitting in the data of a real telescope pointed at a real planet that the next few years of observation are actually going to resolve one way or the other. For nearly the entire history of astronomy, that kind of question could only be asked in theory, argued about in journals, with no real prospect of ever getting closer to a resolution. Right now, for the first time, the resolution is scheduled. Think about what that actually represents, set against the full span of human history. For as long as people have looked up at the night sky, the question of whether anything else out there is alive has been purely philosophical. A question for poets and priests, and eventually science fiction writers, because there was never any way to actually go check. That changed quietly and without much fanfare, sometime in the last few years, the moment a space telescope became sensitive enough to catch a handful of stray molecules in the atmosphere of a planet orbiting a star we can't even see without a telescope of our own. Nobody rang a bell when that threshold was crossed. There was no announcement that said, starting today, this question has a real, testable answer coming. It just happened quietly in the background of ordinary observing schedules and peer-reviewed papers, and now it's simply true. Whether or not K218b turns out to be the specific planet that settles it, the question itself has moved out of philosophy and into an actual observing queue. Webb is going back, the sigma will move, up or down, and either direction will tell us something real. And somewhere around a small red star, 124 light years from here, a signal that might be nothing more than sunlight hitting sulfur in a hydrogen sky, or it might be the first real trace of life beyond our own planet ever detected, is still sitting there in the starlight, unresolved for now, waiting for enough data to finally decide which one it is.